So good afternoon, everyone. I hope all of you are fine. So before starting today's topic, let us see what are the things that we have completed. After that, today we are going to start very short answer type questions. So let us see what are the things that we have already finished till now. We are done with long answer type questions. We are done with long answer type questions from which chapters? First, we have discussed current electricity. Next chapter that we have discussed was nuclear physics. And yesterday, we have seen one more chapter that was wave. These are the chapters that we have completed for long answer type questions. So further, I will be discussing numericals from the above topics. Important numerical from the above topics once we are done with short answer type question. Very short answer type question. Next, we have discussed regarding short answer type. And in this short answer type, what are the chapters that we have discussed? We have discussed regarding semiconductor devices, And what was the next chapter that we have discussed? We have discussed regarding electric charges and field. Then we have discussed regarding electric potential and capacitance. Electric potential and capacitance. Then we have discussed one more chapter that was ray optics. Then we have discussed regarding wave optics. Then we have discussed moving charges and magnetism. And magnetism. What was the next topic that we have discussed? We have discussed regarding seventh one, atoms. And next we have discussed regarding what is that? Electromagnetic induction. Electromagnetic induction. So these are the topics that we are done with. Now again, from this 8 topics, if you are perfect with any 6 chapters, that would be more than sufficient for writing all the 6 answers for your annual examination. So whatever 6 chapters you feel easy, please go through the 6 chapters. Now we are going to start very short answer type question. Very short answer type. So what are the chapters that we'll be discussing? So today I will try to discuss 2 chapters. First, I will start with semiconductors. Then we'll be discussing dual nature of matter. Then we'll move on to the next chapter that we'll be discussing will be magnetism and matter. Then we'll be discussing electromagnetic waves. Then we'll move on to alternating current. Then we'll discuss regarding moving charges and magnetism. Then we'll be discussing regarding ray optics. So from here, we'll be getting one question. Already we have discussed one more chapter. What was that chapter? We have discussed from communication system. Communication system. This chapter we have already discussed. So here, from here, you will be getting one general trend of question paper from, if I observe the last 5 to 6 year question paper, I have seen that from semiconductor, we are getting one question. From dual nature of radiation and matter, we are getting 2 questions. From magnetism and matter, we are getting around 2 questions. And from EM waves, we are getting 1. AC, we are getting 1. Moving charges and magnetism, we are getting 1. Ray optics, we are getting 1. And communication system, we are getting 1. So how many these questions are there? 3, 4, 5, 6, 7, 8, 9, 10. So these are the chapters which we are going to discuss for very short answer type questions. So let us start today's class with semiconductor devices. As we have discussed already, SAQs of semiconductor devices, so it will not be a difficult task for you to revise those things because all the things will be same. So the first question that we'll be discussing in semiconductor devices will be a basic question. What is that? What are intrinsic and extrinsic semiconductors? Already we have discussed this thing. But now we are going to discuss in very short answer type questions. So what will be that? Semiconductor devices. Semiconductor. We are going to discuss regarding which type of questions? Very short answer type questions. The first question that we'll be discussing is, what are intrinsic and extrinsic semiconductors? Intrinsic and extrinsic semiconductors. So what is the first question that we are going to discuss? We are going to discuss regarding intrinsic and extrinsic semiconductor. I said that materials are classified into 3 types: insulator, conductors, and the next one is what? Semiconductors. And which type of element will be what are the elements that will be considering like a semiconductors? Generally, we consider silicon and germanium as semiconductors. So the pure form of silicon and germanium are called as intrinsic semiconductors. So I can write pure form of silicon and germanium are called as which type of semiconductor? Intrinsic semiconductors. SE represents what? SE represents intrinsic semiconductor. Next, I say already we have discussed regarding extrinsic semiconductor. How we are getting extrinsic semiconductor? By doping. What is the meaning of doping? The process of adding impurities called as what? Doping. When we are doping a pure semiconductor, which type of semiconductors will we be getting? We'll be getting extrinsic semiconductor. Further, we have discussed how many types of extrinsic semiconductors are there. That will become our next question. So see here, what is the meaning of doping? This question is not there, but still remember, what is the meaning of doping? Doping. What does it mean? The process of adding impurities to a pure semiconductor, or you can also write intrinsic semiconductor, is called as what? Doping. The process of adding impurities to a pure semiconductor is called as what? Doping. Or you can also write intrinsic semiconductor. Now, what is the meaning of extrinsic semiconductor? So, doped semiconductors are called as extrinsic semiconductors. Semiconductors. So I hope you will remember this. Many times they have asked this question, what are intrinsic and extrinsic semiconductor? What is an intrinsic semiconductor? Pure form of germanium or silicon are called as intrinsic semiconductor. And what are the extrinsic semiconductor? Doped semiconductors are called as what? Extrinsic semiconductor. What is the meaning of doping? The doping represents what? The process of adding impurities to pure semiconductor. Which type of impurities will be adding? Will be adding trivalent impurities, will be adding pentavalent impurities. Depending on impurity concentration, whether it is trivalent or pentavalent, will be getting other two types of semiconductors in extrinsic semiconductors. Now let us discuss regarding extrinsic semiconductors, which will become our next important, very short answer type question for the examination. So we know that what are the extrinsic semiconductors? See here. What is the next one? Extrinsic semiconductors. Extrinsic semiconductors. See here. Again, if you want, you can write the definition. What was the definition for extrinsic semiconductor? Doped semiconductors. Doped semiconductors. Now, based on the doping concentration, we'll be having another two types of semiconductors in what? Extrinsic semiconductor. What are those semiconductors? Let us see. First one is called as P-type semiconductor. P-type semiconductor. I hope you remember this. We have already discussed regarding this. How a P-type semiconductor is formed? When a pure semiconductor, or you can also write intrinsic semiconductor, your wish. When a pure semiconductor is doped with which type of impurities? I said that in P-type, which type of impurity will be adding? Will be adding trivalent impurity. Which type of impurity? Trivalent impurity. So when a pure semiconductor is doped with trivalent impurity, we get P-type semiconductor. So already we have discussed regarding this. Whenever we are adding trivalent impurity to a pure silicon or germanium, which type of semiconductors we'll be getting? We'll be getting P-type semiconductors. What is the meaning of trivalent impurities? Means the element which we are considering, that atom or element must have 3 valence electrons in its outermost orbital. So what are the majority and minority charge carriers? In case of P-type semiconductors, majority carriers and minority carriers. Minority carriers. So what are majority and minority charge carriers in P-type semiconductor? So the majority charge carriers will be holes. Remember this. Many times they have asked this question. What are the majority charge carriers in P-type semiconductor? Holes. And what are the minority charge carriers? These are electrons. Electrons. So I hope you will write this question in the examination. You'll be getting the question something like this. What is a P-type semiconductor? What are majority and minority charge carriers in case of P-type semiconductor? I hope you understood this. Let us move on to the next question. In extrinsic semiconductor, one we have discussed regarding P-type semiconductor, and the other semiconductor will be N-type semiconductor. N-type semiconductor. So again, We'll be getting N-type semiconductor by doing doping, but which type of doping, which type of element impurities we should add? Here we should add pentavalent impurities. So what is the answer we have written here? Here we have written when a pure semiconductor is doped with which type of impurity? Trivalent impurity, will be getting P-type semiconductor. So here what I'm supposed to write? When a pure semiconductor is doped with pentavalent impurities, we get N-type semiconductor. N-type what? Semiconductor. Remember, for N-type semiconductor, which type of impurities will be adding? We'll be adding pentavalent impurities. So in order to get N-type semiconductor, which type of impurities will be adding? We'll be adding pentavalent impurities. So what are the majority and minority charge carriers here? Majority charge carriers. Majority charge carrier, and next we'll be having minority charge carrier. Minority charge carrier. So what are the majority and minority charge carriers in case of P-type and N-type semiconductor? In case of N-type semiconductor, electrons will be majority charge carriers. Electrons will be majority charge carriers, and holes will be minority charge carriers. And holes will be minority charge carriers. So what are the things that we have discussed? We have discussed regarding intrinsic and extrinsic semiconductor. How an intrinsic semiconductor is formed. An intrinsic semiconductor is nothing but a pure form of silicon or germanium. When we are doping that pure semiconductor, which type of semiconductor we will be getting? We'll be getting extrinsic semiconductor. In based on the impurities, when we are adding trivalent impurity, we'll be getting P-type semiconductor. When we are adding pentavalent impurity, we'll be getting N-type semiconductor. In P-type semiconductor, what are the majority and minority charge carriers? In case of P-type semiconductors, we'll be having holes as majority charge carriers and electrons as minority charge carriers. Whereas in case of N-type semiconductors, we'll be having electrons as majority charge carriers and holes as minority charge carriers. I hope you understood these two things. These are very much important questions, most important questions for your examination. So let us move on to the next important question from this particular chapter, that is, what is a PN junction diode and what is the depletion layer? So we know that, what is that? This one is third one. So PN junction diode. How a PN junction diode is formed? This we have already discussed. Let us see. If we consider a pure semiconductor, one part of which I have doped with pentavalent impurity, what? Pentavalent impurity, and the other part I have doped with trivalent impurity. So let us see. I have doped this region, with trivalent impurity, and this region I have doped with pentavalent impurity. So I have considered a pure semiconductor. To that pure semiconductor, half of the part I have doped with trivalent impurity, and the other half part I have doped with which type of impurity? Pentavalent impurity. So the region which I am doping with trivalent impurity, which region I will be getting? I will be getting a P region. I will be getting which region? A P region. And the region where I am doping with pentavalent impurity, which type of region I will be getting? I will be getting N-type semiconductor, N region. So this is the formation of p-n junction diode. So how you should write the answer? When a pure semiconductor is doped in such a manner that half part is doped with p-type impurities, sorry, trivalent impurities, and the other half part is doped with pentavalent impurities, then we'll be getting which type? What we'll be getting? We'll be getting a p-n junction diode. So in between the p-n junction diode, a region is formed. Here a region is formed which is depleted of charges. If I go on explaining this, how this is formed, it will become a very large topic that is not necessary. Just remember, in a p-n junction diode, there is a region which is depleted of charges. That region is called as the depletion region. Depletion region. And what is the symbol for p-n junction diode? The symbol for p-n junction diode is given as, this is a triangle. This is the symbol for p-n junction diode, and this terminal is p terminal, and this terminal is n terminal. This terminal is n terminal. So what is a p-n junction diode? It is a two-terminal device. How it is formed? When a pure semiconductor is doped in such a manner that half part is doped with trivalent impurity and the other half part is doped with pentavalent impurity, which type of semiconductor will be getting? Sorry, which type of diode will be getting? We'll be getting a p-n junction diode. So in p-n junction diode, there is a region. That region is depleted of charges, and that region is called as what? That region is called as depletion region. I hope you understood what is the small definition for p-n junction diode and depletion region. So now let us discuss the next important question based on p-n junction diode is, forward and reverse bias. Fourth important question is forward bias and reverse bias p-n junction diode. Forward bias p-n junction diode. Another important question, many times they have asked in the examination, what is the meaning of forward bias p-n junction diode? Now carefully see here. Let me consider a p-n junction diode. This is my p-n junction diode. This is which region? P-type terminal or n-type terminal? This is p-type terminal. And this is which type of terminal? This is n-type terminal. When p terminal is attached to the positive terminal of the battery, when p region or p terminal is attached to a positive terminal of the battery, and n terminal is attached to a negative terminal of the battery, then this type of arrangement is called as what? Forward bias p-n junction diode. So in case of forward bias p-n junction diode, how is the arrangement? When the p terminal of a p-n junction diode is connected to positive or high potential of the battery, and the n terminal of a p-n junction diode is connected to low potential of the battery, then this type of arrangement is called as what? Forward bias arrangement. See here, I will discuss one more important thing here. Try to understand. See here, let us assume this is my p-n junction diode. This is my p-n junction diode. This is my p-n junction diode. This here I am having p terminal, here I am having n terminal. To this p terminal, what I did, I have attached high potential of the battery, and to this n terminal, what I did, I have attached low potential of the battery, negative. Now this region is called as, which region we have already discussed. This region is called as depletion region. Depletion region. So in case of forward bias, what will happen to the width of the depletion region? Whether the width of depletion region decreases or it will increase, let us understand. See here. Now, in P set, what are the majority charge carrier? In P set, we are having holes as majority charge carrier. In N set, what are the majority charge carrier? In N set, we are having electrons as majority charge carrier. Can the electron come towards negative terminal of the battery? No. Can these holes come towards positive terminal of the battery? No, because electrons are which type of charge carrier? They are negative charge carrier. So negative charge and negative terminal of the battery, they will attract or repel, they will repel each other. So what will happen? Electron will try to go towards P region, and here holes will try to come towards N region. So what will happen in case of forward bias PN junction diode? The electrons can't flow towards the negative terminal of the battery. Holes can't flow towards the positive terminal of the battery, due to which what will happen? Electron tries to cross this depletion region and go to P side, and what holes will do? Holes will try to move towards N region. Due to that, what will happen? The width of the depletion region decreases. So important point and important question. You will be getting the question. In case of forward bias, what will happen to the width of a depletion region? So what you are supposed to write? The width of depletion region, decreases in case of which bias? Forward bias. In case of forward bias, the width of depletion region decreases. In case of which bias? In case of forward bias. Remember this. The width of depletion region decreases in case of which bias? Forward bias. So what is the meaning of forward bias PN junction diode? When P terminal of a PN junction diode is connected to high potential of the battery, and N terminal of a PN junction diode is connected to low potential of the battery, then we'll be getting which type of junction? We'll be getting forward bias PN junction diode. So what will happen to the width of depletion region in case of PN junction forward bias PN junction diode? The width of depletion region decreases in case of forward bias. So let us discuss about reverse bias. Next one is what? Fifth one. Reverse bias PN junction diode. PN junction diode. I hope you will directly write this answer without teaching anything, because in case of forward bias, what happened? P terminal is connected to positive terminal of the battery, N region is connected to negative terminal of the battery. So here it will be reverse. So here let us consider a P terminal. This is our PN junction diode. Here we are having which type of terminal? Here we are having N terminal. This is P terminal. When P terminal of the battery, when P terminal of a PN junction diode is connected to low potential of the battery, and when N terminal of the PN junction diode is connected to high potential of the battery, then this type of arrangement is called as what? Reverse bias PN junction diode. So let us see what will happen to the depletion region or width of depletion region in case of reverse bias PN junction diode. See here. So here let us consider this is P region. Here I am having N region. The P terminal of that PN junction diode is connected to negative terminal of the battery, and positive terminal of the battery is connected to N terminal of a PN junction diode. So this region is called as which region? This region is called as depletion region. Depletion region. This region is depleted of what? Charges. Now see here, what will happen to the width of this depletion region in case of reverse bias? See here. This P side is connected to negative terminal of the battery, N side is connected to positive terminal of the battery. So the electrons can easily go towards positive terminal because positive and negative charges will attract. So electron can easily go to the positive terminal of the battery, and P will be having holes. Holes are nothing but, we assume it to be positive particles, positive charges. So holes can easily come towards negative terminal of the battery, because here it is, we are having negative, and here for P will be having holes. We are assuming holes to be positive charge particles. Here electrons are negative charge particles. They can easily move towards which terminal? Positive terminal. So due to this, what will happen? This width will increase. The width will increase. So remember, width of depletion region increases in case of what? Reverse bias. Remember this. So in case of forward bias, the width of depletion region decreases. Whereas in case of reverse bias, width of depletion region increases. Width of depletion region increases. I hope you are getting this. So what are the things that we have discussed? We have discussed regarding PN junction diode, how your PN junction diode is formed. And further, what we have discussed, forward bias PN junction diode and reverse bias PN junction diode. What is the meaning of forward bias PN junction diode? When P terminal of a battery is connected to positive terminal of the, when P region of a PN junction diode is connected to positive terminal of the battery, then we'll be getting which type of PN junction diode? We'll be getting forward bias PN junction diode. Next, if we connect P terminal of a PN junction diode to the negative terminal of the battery, then we'll be getting which type of PN junction diode? We'll be getting reverse bias PN junction diode. In case of forward bias PN junction diode, what will happen to the width of depletion region? The width of depletion region decreases in case of forward bias. And what will happen to the width of depletion region in reverse bias? The width of depletion region increases in case of reverse bias. Now see here, as an application for PN junction diode, we have discussed regarding rectifier. What is the meaning of rectifier? A device which converts AC to DC AC voltages to DC voltages. That process is called as rectification, and the device used for that is called as what? Rectifier. Then we have discussed regarding two rectifiers. What are those two rectifiers? One rectifier was half wave rectifier, and the other rectifier was full wave rectifier. So just you are supposed to remember the efficiencies of half wave and full wave rectifier. So next question will become efficiency of half wave and full wave rectifier. Half wave rectifier. So what was the efficiency of half wave rectifier? I hope you remember that efficiency of half wave rectifier was given as 40.6%. Efficiency of half wave rectifier is given as what? 40.6%. And what was the efficiency of full wave rectifier? Full wave rectifier. Full wave rectifier. And what was the efficiency of full wave rectifier? The efficiency of full wave rectifier was how much? 81.2%. I hope you remember this. I've clearly explained the how an half wave and full wave rectifier work. So what is the efficiency of half wave rectifier? The efficiency of half wave rectifier is 40.6%. And what is the efficiency of full wave rectifier? The efficiency of full wave rectifier is how much? It is 81.2%. So I hope you understood. You will remember this thing. Now let us discuss regarding one more diode that is called as Zener diode. So in the examination, you will be getting the question for Zener diode. Why we will be using Zener diode, how it is connected. So next one is Zener diode. Zener diode. So what is Zener diode? It is a heavily doped PN junction diode. What is Zener diode? It is a heavily doped PN junction diode. In which bias it will be used? It is used in reverse bias condition. It is used in which type of bias? Forward bias or reverse bias? In forward bias, it will just behave like a normal ordinary PN junction diode. But in case of reverse bias, it will give some other behavior. We'll be using this Zener diode in case of voltage regulators. We use Zener diode. So where we'll be using this Zener diode? We use it in which devices? Voltage regulators. Voltage regulators. So what is a Zener diode? Zener diode is nothing but a heavily doped PN junction diode. In which bias it will be used? It will be used in reverse bias. What will happen if I use it in forward bias? Nothing will happen. It will work like an ordinary PN junction diode. And where we'll be using the Zener diode? We'll be using the Zener diode in voltage regulator. So what is the symbol for this? The symbol for this Zener diode is given as something like this. Here we'll be having a triangle, and here we'll be having Z symbol, something like this. Z symbol. That represents Zener. So here this region is N region, this region is which region? P region. So this is the symbol for what? Zener diode. Zener diode symbol. So I hope you will remember this point. So what is a Zener diode? It is a heavily doped PN junction diode. In which bias we'll be using? It will be using this in reverse bias. And where we'll be using this? This will be used in what? Voltage regulator, in order to get constant output voltage. Whenever the input power or input voltage is fluctuating, but still if I want to get the constant output voltage, which what we'll be using? We'll be using voltage regulator. So in voltage regulator, what is there? In voltage regulator, we'll be having a Zener diode. You might have seen that in olden days, we used to use these voltage regulators in order to protect the devices like TV, televisions, and fridges. Nowadays, you will be able to see these voltage regulators nearby ACs. See here. Now let us discuss the next important question from this semiconductor devices, and that is circuit symbol for NPN and PNP transistor. So, what is that question? How many questions we have discussed? 8. Next one is circuit symbol for first one. PNP transistor and the second one is NPN transistor. Transistor represents transfer of resistance. So transistor is a how many terminal device? It is a 3-terminal device. Transistor is a 3-terminal device. What are the 3 terminals? Emitter, base, and collector. So a transistor consists of how many terminals? 3 terminals. How many types of transistors we are discussing? We are discussing 2 types of transistors. What are those? NPN and PNP transistors. So we are supposed to draw the circuit diagram for circuit symbol for what? PNP and NPN transistor. So remember this circuit diagram. So in some books, the diagram is given in a wrong manner. Please try to draw the diagram something like this. So here we'll be having 3 terminals. Here we'll be having how many terminals? We'll be having 3 terminals. So this terminal is called as base terminal. What is this terminal called as? This terminal is called as base terminal. And we'll be having one more terminal that will be called as, from here I will be drawing one terminal. So from here, we will be having other 2 terminals. One terminal is called as emitter terminal. Other terminal will be called as collector terminal. What is this? This terminal is called as what? This terminal is called as emitter. And here I am writing what? Here I am writing collector. So the important thing in this PNP and NPN transistor is the symbol, direction of the symbol, whether the current is flowing inside or it is going outside. So see here, in case of PNP transistor, the direction will be downwards. Here, the current will flow from emitter region, something like this. So how to remember, sir, means what you can do is that if I Let me consider this one. Collector. So what was the direction? This was the direction. How to remember this are because in case of NPN transistor, the direction will be in opposite direction. So how to remember this means just a technique for remembering this. Remember this thing. So what is the transistor? This one is P, NP transistor. Cut this P region. So we know that this is positive terminal, this is negative terminal. We are going from positive to negative. We are going from what? Positive to negative. So we are going from outside to inside. I am coming from what? Outside to inside. So similarly, if I see NPN transistor, if I try to draw the NPN transistor, so let us see whether I am able to take this or copy this. Yeah. So let me consider this one. So here, what will be the direction here? Let us see. What will be the direction? What I said? Which type of transistor it is? NPN. Cut the first thing. Now it is going from P to, I am going from positive to negative. So it is going from inside to outside. I am going from where to where? I am going from inside to outside. So here the direction will be something like this. So if you don't draw the direction properly, then you will be losing the mark. So these are the circuit symbols for what? Transistor. So how to remember this? If you are drawing the circuit symbol for PNP transistor, cut the first thing. Now go from positive to negative. So P region is outside. From outside to, we are coming in inside region. Similarly for NPN transistor, if you cut the first thing, we should go from positive to negative. P is inside and we are going outside. So here the direction will be outside. So see here, what are the three terminals in a transistor? We'll be having emitter, base, and collectors. And how many types of transistors we are having? We are having two types of transistor. What are those? PNP and NPN transistor. I hope you understood this. And you will remember this circuit diagram. Very important for your examination. So next question is, what is an amplifier? You might have heard about this word amplifier, isn't it? So this is also connected to a big device that is called as amplifier. So whatever I am talking, that voice is being amplified and it is being projected outwards. So that is nothing but what is amplifier? Amplifier is a device which is used to increase the strength of the signal. So what is amplifier? Amplifier is a device which is used to increase the strength of the signal. The next one, what is the next question? I think 11th. Yeah, 9th, 10th. What is the next important VSPQs? Amplifier. What is an amplifier? It is a device. It is a device. Why do we use this device? To increase the strength of a signal. So what is an amplifier? Amplifier is a device which is used to increase the strength of a signal. So let us move on to the next question. Next question we have already discussed. What is that? Very easy question. 11th question we are going to discuss is, what are the universal logic gates? Universal logic gates. Universal logic gates. So we know that generally we have discussed the three types of gates. What are the gates? AND gate, OR gate, NOT gate. Those are the fundamental gates, basic logic gates. And what are the combinational gates we are having? NAND gate, which is a combination of AND gate and NOT gate. And we'll be having NOR gate, that is the combination of OR gate and NOT gate. So what are the universal logic gates means? What are those universal logic gates? First one is NAND logic gate. NAND logic gate. And the next universal logic gate is what? Next one is NOR logic gate. NOR logic gate. So what are logic gates? Logic gates are nothing but electronic devices which are used for performing arithmetic operation or mathematical operations. Based on that mathematical operations, we'll be having and, or, and not logic gate. By using and logic gate, which type of mathematical operation we'll be performing? We'll be performing and multiplication operation. By using or logic gate, which type of mathematical operation we'll be performing? We'll be performing addition operation. And by using not logic gate, which type of operation we'll be performing? We'll be performing inversion. It will invert the things. So I hope you will remember this. And the last question, which we'll be discussing from the semiconductor devices is, what is the difference between NAND gate and NOT gate? Sorry, NAND gate and AND gate. Already we have discussed this. So see here. Last question, I think 12th question. Yeah. 12th question. What is that? I am writing AND logic gate. And logic gate. And here I am writing NAND logic gate. NAND logic gate. This is the last question from semiconductor devices. So what is the symbol for AND logic gate? I said that AND logic gate consists of two terminals and the symbol will be D, and it will be having one output terminal and two input terminal. If the inputs are A and B, what will be the output? Output will become Y is equals to A dot B. Output will become what? A dot B. And what will be the symbol for NAND logic gate? Again, NAND logic gate will also consist of two terminals. And the symbol for NAND logic gate will be a D symbol with a bubble. So here I am having two inputs. This is input A. This is input B. And what will be the output? Output will be Y is equals to A dot B bar. So whatever the outputs I will be getting for AND logic gate, that will be inverted by which logic gate? That would be inverted by NAND logic gate. So what is the truth table? So the truth table for which type of logic gate? AND logic gate. So how many inputs we'll be having? We'll be having two inputs. And how many output will be there? Only one output will be there. What is that output? Y is equals to A dot B. And how many inputs we are having? We are having two inputs. What are those inputs? A, B are the inputs. So let us see the mathematical operation performed by what? AND logic gate. So when the input, both the inputs are 0, output will also be 0. When any one of the input is 1, output will be 0. Here also, if I am taking input A as 1 and input B as 0, again the output will be 0. But if I take input A as 1, input B as 1, and what will be my output? My output will become 1. So in case of AND logic gates, where output will be 1 only when both the inputs are 1. Now let us see the truth table for NAND logic gate. Truth table for which logic gate? NAND logic gate. So how many inputs we are having? Here also we are having two inputs. And how many outputs we are having? Here also we are having only one output. See here, what are the inputs? The inputs are A, B. And what is the output? Output is Y is equals to A dot B bar. A dot B bar. So let us see what will be the outputs here. When both the inputs are 0, output will be 1, because 0 into 0 will become 0. Here, whatever the output I am getting, that will be inverted here. So here 0 input A and 1 input B, actually 0 into 1 will become 0, but here we are having bar. So here we'll be getting 1. So whenever input A is 1, input B is 0, again I will be getting 1. But when the both the inputs are 1, what will be the output I will be getting? I will be getting the output as 0. So what does a NAND, and what is the difference between NAND and AND logic gate? the NAND logic gate will invert the output of AND logic gate. So here, see here, what is the output I am getting? Here I am getting the output as 0. But in case of NAND logic gate, what is the output I am getting? I am getting the output as 1. So when both the inputs are 1, here output is 1. But here when both the inputs are 1, the output is 0. So it works in inverse manner of AND gate. So by this, we finish all the important SAQs from which chapter? From semiconductor devices. So let us move on to the next important VSAQ chapter that we'll be discussing is dual nature of radiation and matter. So I don't think we'll be able to complete that entire chapter today, but at least let us discuss 2 questions from that chapter. So these are the important VSAQs from semiconductor devices. So what is the first thing we have discussed? We have discussed regarding intrinsic and extrinsic semiconductor. Then we have discussed regarding P-type and N-type semiconductor. Then we have discussed regarding PN junction diode and what is the forward PN junction diode and what is reverse bias PN junction diode. Then we have discussed regarding the efficiencies of rectifier. Then we have discussed regarding a new diode that is called as Zener diode. Then we have discussed regarding transistor. How many types of transistors we are having? We are having 2 types of transistor, NPN and PNP transistor. Then we have discussed regarding amplifier. What is an amplifier? It is a device which is used to increase the strength of a signal. Next, we have discussed regarding universal logic gates. Which type of gates are called as universal logic gates? NAND gate and NOR gates are called as universal logic gates. So let us discuss. Let us start the next chapter, next important VSAQ chapter, that is dual nature of radiation and matter. Dual nature of radiation and matter. Radiation and matter. So first we'll be discussing very basic questions from this. There are 2 basic questions. What are those questions means? Write down the expression for de Broglie wavelength. And what is the next very important easy question? Write down the expression for Einstein photoelectric effect. Write down the expression for what? Einstein photoelectric effect. So first of all, we'll be discussing regarding equation for or formula for de Broglie's wavelength. De Broglie's wavelength. Very important question. So I hope everyone know what de Broglie said. That de Broglie said that whenever an electron is revolving around the nucleus, along with that electron, a wave is associated. That wave is called as which type of wave? That wave is called as matter wave. And the name for that matter wave was given by de Broglie. So that wave, the wavelength is called as what? De Broglie wavelength. So what is the formula for that? The de Broglie wavelength is given as lambda is equals to h divided by p, where h is, what is h? This is called as Planck's constant. And what is p? P is called as momentum of the particle. Or you can also write this formula as lambda de Broglie is equals to h divided by, what is the value of p? The value of p is mv, where m is mass of the particle and v is the velocity of the particle. What is m? M represents mass of the particle and v represents velocity of the particle. So this is important question for 2 marks. For writing the formula, you will be getting 1 mark. And for explaining the terms, you will be getting 1 mark. So what is that question? The question is write down the formula for de Broglie wavelength. So what de Broglie said? De Broglie said that whenever an electron is revolving around the nucleus, what will happen? along with that electron, a wave will be associated. That wave is called as what? That wave is called as de Broglie wave. Or that wavelength is called as what? De Broglie wavelength. Let us move on to the next important question from this chapter. That is second one. Einstein's photoelectric effect Einstein's photoelectric equation. Einstein's photoelectric equation. Einstein's photoelectric equation. So here, what is Einstein's photoelectric equation? We know that photon energy, I can explain what is Einstein's photoelectric effect. We'll discuss that tomorrow. Photon energy is equals to work function plus kinetic energy. Or you can also write what is the energy of photon? E is equals to h nu is equal to work function. I'm writing with W. And what is the expression for kinetic energy? 1/2 mv square. Or you can also write the kinetic energy of electron emitted or the particle emitted is given as mv square is equals to h nu minus W. So whatever, if you want to write this equation, you can write this equation, or if you want to write 1/2 mv square, you can write that equation, your wish, or any of the equations you can write. So let us finish today's class here itself. So we have discussed regarding important VSQs from semiconductor devices, and we have started what dual nature of radiation and matter. Please remember that from dual nature of radiation matter, every year from past 4 or 5 years, we are getting 2 VSQs. I think there are around 7 VSQs. Out of those 7 VSQs, we'll be getting 2 VSQs in our annual examination. So I hope you will go through all these questions. We'll meet tomorrow. Thank you.